Hello and welcome to another one of D's ADD videos. Today we're going to be looking at some basic examples of determining whether a molecule is polar or not. So first things first, you need to be able to draw your Lewis structures and determine your Vesper theory pretty easily by now, hopefully. If you were to look at beryllium chloride and you did your electron count, you should get something like this for the Lewis structure. And then when you did Vesper theory, you should predict a linear molecule. Okay? So let's discuss the bond between beryllium and chloride. The chlorine element is way up here to the top right, so it's very electronegative, whereas beryllium is way over here, so it's not nearly as electronegative. What does that mean? That means that the electron density is far greater around the chlorine than it is around the beryllium. The probability of finding the electrons in this bond around the beryllium are much less than around the chlorine. That results in a negative charge here, a positive charge there. The dipole looks like this, but what you got to realize is the dipole in this direction is canceled out by the dipole in that direction because of the 180-degree bond angle. This is symmetric. So even though there's polarity, it's symmetric, and therefore it's going to be a non-polar molecule. And the Mg and the EPG were both linear. Let's look at water. Water, you should remember, if you've done this already, you should look at the Lewis structure as something like that. And that's 4 domains for the central atom. 2 are bonds and 2 are lone pairs. That you'll find is an EPG of tetrahedral, and the Mg of bent. So when we're looking at this, the hydrogen-oxygen bond is very polar. This is a lot more electronegative than this guy. If you look at the periodic table, oxygen is right there, whereas hydrogen's way over here. So an asymmetry of charge develops. Electron density looks something like that. And then what happens is you get a dipole moment. That's drastically enhanced by these electrons here. Now, if you were to break this up into the components, you would have one component for each going up, and they would reinforce each other. So the horizontal components will cancel, making the overall compound polar. If you were to draw it three-dimensionally, where this bond angle is less than 109.5, I believe it's 104.5, but these electrons push the bonding electrons away from each other, or from them closer to each other. Okay, so then let's look at this final example, carbon tetrachloride. Again, if you did the Lewis structure, you would end up with something like this. And then the 4 domains, 0 lone pairs, is going to be both an EPG and a Mg of tetrahedral. Now the problem with this one, even though the carbon-chlorine bond is very polar, if you look at the periodic table, carbon and chlorine's a lot more electronegative than carbon. What results is a symmetry because all the bond angles are 109.5. All the dipole moments that are created cancel each other out. There's one there that's canceled out, and that one there, that one there. All their components will cancel out. Why? Because there's symmetry. Again, even though there's polar and polar bonds, but because there's symmetry, it's non-polar. Okay? So practice, practice, practice. Hopefully this has cleared up some doubts as to symmetry questions. Check out the more advanced video that'll be coming up after this one. Thank you and have a nice day.